This is a problem involving simultaneous translation and rotation for Learning Goal RM6. We're given that a solid sphere of mass m, so it's going to be general case, and radius r, starts at rest on a 30-degree slope, rolls 4 meters down the slope, and then rolls away on level ground. And the problem we're trying to solve is how fast is it going, what is its linear speed or its translational speed as it rolls away from the incline. This is a conservation of energy question. We will begin, as with all such questions, with a system diagram. So I've drawn in our slope. This is the 4 meters from top to bottom along the incline. And the two positions we're interested in here are at the top of this slope when it's at rest, and at the bottom as it's rolling away. So we can label those position A and position B. Now on your system diagram, you should also write down what you've been given, what you can presume, and what you need to find. So in conservation of energy, you know you're interested in gravitational potential energy, so you need to know the height at each point. You generally assume that the lowest height in the problem is 0. So we'll make that at the bottom of the slope. At the top of the slope, the height, we just have a little bit of trig to do here. This is the height that you need, and you can see it's the opposite side of this 30-degree angle. Where 4 meters is the hypotenuse. So at this point, the height would be 4 meters. Okay, it's opposite, so sine of 30 degrees, which means it's 2 meters. For the speed at the top, it begins at rest. At the bottom, the speed is what we're trying to find out. And now here's the new piece. Because it is rolling motion, we're not just interested in its translational speed, but also its angular speed, omega. So at the top of the slope, it's not moving, so omega is 0. At the bottom, omega is an additional unknown that wasn't mentioned in the question. So there's the general idea. So then we will draw our LOL, our energy bar diagram. Start by identifying the system, which is this sphere. And because it's interacting with the Earth as its height changes, the Earth is also part of the system. There's no work in or out, no forces applied, no friction to consider. So for the energy bar diagrams, we need to consider all the relevant types of energy. Gravitational potential energy, kinetic energy, and now, because you've got rotation, your rotational kinetic energy. And these will all add up to the total mechanical energy. And same after. So if this is position A and this is position B, EG plus EK plus our K rotational make ET. All right, so starting out, all our energy is gravitational potential energy. There's no kinetic energy, no rotational kinetic energy. All the energy is EG. But at the bottom, you're down to height level 0, so you've got no gravitational potential energy. The total energy is the same as it was. And this is now some mix of kinetic energy and rotational kinetic energy, and we don't know what proportion, but we know that they will add up to more or less, or exactly, the total energy. So from the energy bar diagram, we can write our big energy equation. And we see that the gravitational potential energy at A must be the sum of the kinetic energy at B and the rotational kinetic energy at B. So gravitational potential energy is mgh at A, a half mvb squared, and a half I omega squared. All right. Before we carry on, I'll remind you, and you'll have this available to look up, that for a solid sphere, the moment of inertia is 2/5 mr squared. And the other important thing here is the link between translational speed, the linear speed of the center of mass, and the angular speed. And that is, and you've seen this before, v is equal to r times omega. This is in a situation where we've got a rolling object known as the rolling condition. This is only true if an object is rolling without slipping, which will be the case in any problem that you have. So now we just have a lot of algebra to deal with. Our sphere has a mass of big M, so I'll write in big M. And we're just going to keep everything symbolic to the end. So a half mvb squared plus a half. Okay, so your sphere, moment of inertia, 2/5 mr squared, plus, okay, now we want to solve for v, which is why I left v here, and we're going to express omega in terms of v. Our rolling condition leads us to omega b, there, I should have written a b there, is equal to the v at point B divided by the radius of the sphere, which is big R in this problem. So plus our half I. Now let's erase that. I just need to write for omega b. It's VB over R squared. Okay. So mg HA equals 1/2 m VB squared plus, let's cancel the 2's here. You see you've got r squared, and you're going to have r squared on the bottom there because the squared applies to everything. So we have 1/5 m VB squared. And so these are like terms. If you get a common denominator, 5/10 and 2/10 is 7/10 m VB squared. Alright, well, we'd already canceled out our radius of the sphere. You now see that the mass of the sphere is irrelevant also. And now we can solve for VB. VB squared will be g. The starting height, which we had found to be 2 meters. And then that's divided by 7/10. And if you solve that, VB comes out to be 5.3 meters per second, which was what we were trying to find. What is the sphere's linear speed as it leaves the incline? Therefore, the sphere leaves the ramp at 5.3 meters per second. Okay. So, to review, system diagram. Find your relevant positions, write down all your knowns and unknowns. In this case, you care about the height, the speed, and the angular speed. Identify your system, draw all your energy bars, your LOL diagram, then take the relevant types of energy, put them into an energy equation, and then go solve. Good luck!